Precipitation is the general term for all forms of moisture originating from clouds and falling to the ground. It is that portion of the hydrologic cycle in which the atmospheric water vapor is condensed, forming water droplets sufficiently large that gravity causes them to fall to earth. There are some factors determining precipitation. Some of these are the climate, geography, and ocean surfaces. Ocean surfaces is the chief source of moisture for precipitation. Moving on to its forms, there are two types of precipitation. These are liquid and solid precipitation. In liquid precipitation, the most common examples are drizzle and rainfall. Comparing these two, drizzle is a fine sprinkle of small and rather uniform water drops that have a diameter less than 0.02 inch. To qualify as a drizzle, the drops must not only be small, but they must also be numerous. Raindrops, as a rule, are larger than a drizzle. On occasion, the drops may be of drizzle size, but they are then few and far between. The other type is frozen precipitation. An example of this is the snow. It is a precipitation of solid water, mainly in the form of branched hexagonal crystals, resulting from condensation of water vapor directly to ice. Although moisture is always present in the atmosphere, but it is condensed only when air is cooled and saturated with some water vapors. Usually, mechanism by which air is cooled to cause precipitation is the lifting of air mass. Based on lifting of air-carrying vapors, precipitation is classified as follows: convective precipitation, cyclonic precipitation, and orographic precipitation. Convective precipitation results from the lifting or upward movement of air that is warmer and lighter than its colder, denser surroundings. Typically, on a hot day, the ground surface becomes heated, as does the air in contact with it. This causes the air to rise, expand, and cool dynamically, causing condensation and precipitation. Cyclonic precipitation results from the lifting of air converging into a low-pressure area, or cyclone. A cyclone is defined as an area of low pressure with a counterclockwise circulation of the air around it, usually inward towards the center. This type of precipitation can also be classified into non-frontal and frontal. Non-frontal precipitation can occur in any kind of barometric depression or barometric low. The lifting of the air is caused by horizontal convergence of air flowing from an area of higher pressure into the low pressure area. On the other hand, frontal precipitation is the result of lifting of lighter warm moist air over more dense cold air. Generally, most storms in the Great Plains states are cyclonic. The third method of lifting an air mass occurs when air flows up and over a topographic feature such as a mountain barrier. Orographic barriers often supply the lift to set off precipitation. For this reason, precipitation is heavier on windward slopes with rain shadows on leeward slopes. Orographic precipitation that is not associated with cyclonic or convective action tends to be of low intensity with relatively long duration.
Rainfall is the most important climatic element in the Philippines. Rainfall distribution throughout the country varies from one region to another, depending upon the direction of the moisture-bearing winds and the location of the mountain systems.
The rainfall is usually characterized by the depth, intensity, and duration.
The depth is important to the overall hydrologic cycle and replenishment of the soil and water. It is the accumulation of rainfall measured by multiplying rainfall intensity and its duration.
Also, the depth may be the same for high-intensity short-duration rainfall as it is for low-intensity long-duration rainfall. The average depth of precipitation over a specific watershed area is more accurately estimated for an area that is well monitored.
The intensity of rainfall is a measure of the amount of rain that falls over time. The intensity of rain is measured in the height of the water layer covering the ground in a period of time. It means that if the rain stays where it falls, it would form a layer of a certain height. Higher rainfall intensity produces larger sized raindrops which have more impact energy, and thus higher intensity storms can damage delicate vegetation and bare soil.
The types of rainfall based on intensity can be classified as light rain, where rate of rain varies between 0 to 2.5 mm, moderate rain, where rate of rain varies between 2.6 mm to 7.6 mm, and heavy rain, where rate of rain is beyond 7.6 mm.
The duration refers to the length of time rainfall occurs. A high-intensity rainfall for a short duration may affect tender seedlings. However, rainfall of longer duration can significantly affect infiltration, runoff, and soil erosion processes.
Statistical methods can be applied to a long time series of rainfall data. These include depth area duration curves, intensity duration frequency curves, probable maximum precipitation, and hyetograph.
The area distribution characteristics of a storm of given duration is reflected in its depth area relationship. For a rainfall of a given duration, the average depth decreases with the area in an exponential fashion given by P bar is equal to P naught e raised to negative Ka raised to the nth power, where P bar is the average depth in centimeter over an area A kilometer squared. P naught is the highest amount of rainfall in centimeter at the storm center, and K and N are constants for a given region.
Preparation of DAD curves involves considerable computational effort and requires meteorological and topographical information of the area. Detailed data on severe most storms in the past are needed. DAD curves are essential to develop design storms for use in computing the design flood in the hydrological design of major structures such as dams.
In hydrology, frequency analysis of station rainfall data is done for use in design of bridges and culverts on highways, design of storm drains, etc. If the rainfall data from a self-recording rain gauge is available for a long period, the frequency of occurrence of maximum intensity occurring over a specified duration can be determined. A knowledge of maximum intensity of rainfall of specified return period and of duration equal to the critical time of concentration is of considerable practical importance in evaluating peak flows related to hydraulic structures. Now, the frequency analysis concept is applied on a seasonal basis and for areal frequency. The rainfall records of deficient length have to be extended by station year method. The results of frequency analysis are plotted on the logarithm by logarithm paper. In the design of major hydraulic structures such as spillways in large dams, the hydrologist and hydraulic engineer would like to keep the failure probability as low as possible. This is because the failure of such a major structure will cause very heavy damages to life, property, economy, and national morale. In the design and analysis of such structures, the maximum possible precipitation that can reasonably be expected at a given location is used. The probable maximum precipitation or PMP is defined as the greatest or extreme rainfall for a given duration that is physically possible over a station or basin. From an operational point of view, PMP can be defined as that rainfall over a basin which would produce a flood flow with virtually no risk of being exceeded. The development of PMP for a given region is an involved procedure and requires the knowledge of an experienced hydrometeorologist. Statistical studies indicate that probable maximum precipitation can be estimated as PMP is equal to P bar plus K sigma, where P bar is the mean of annual maximum rainfall series, sigma is the standard deviation of the series, and K a frequency factor which depends upon the statistical distribution of the series. number of years of record, and the return period.
A hyetograph is a plot of the intensity of rainfall against the time interval. The hyetograph is derived from the mass curve and is usually represented as a bar chart. It is a very convenient way of representing characteristics of a storm and is particularly important in the development of design storms to predict extreme floods. The area under a hyetograph represents the total precipitation received in the period. The time interval used depends on the purpose. In urban drainage problems, small durations are used, while in flood flow computations, in larger catchments, the intervals are of about 6 hours.
Point rainfall measurements. Point rainfall or station rainfall, the rainfall during a given time interval, or often one storm, measured in a rain gauge, or an estimate of the amount which might have been measured at a given point. Moving average technique. Moving average is a technique for smoothing out the high-frequency fluctuations of a time series and to enable the trend, if any, to be noticed. Storms of high intensity and varying durations occur from time to time. However, the probability of these heavy rainfalls varies with the locality. The first step in designing engineering projects dealing with flood control, gully control, etc. is determine the probability of occurrence of a particular extreme rainfall. This information is determined by the frequency analysis of point rainfall data. Frequency analysis deals with the chance of occurrence of an event over a specified period of time. Suppose P is the probability of occurrence of an event rainfall whose magnitude is equal to or in excess of a specified magnitude x. The recurrence interval return period is related to P as follows. Plotting position. There are two methods for performing frequency analysis. Empirical method, frequency factor method, and some of the methods. California method, Hazen method, Weevil method, Figurative method, Bloom method. M is ranked assigned to the data after arranging them in descending order of magnitude. Thus, the maximum value is assigned m equals 1. The second largest value m equals 2. And the lowest value m equals n. N is number of records. Weevil formula. Weevil formula is the most commonly used plotting position formula. Having calculated P and T for all the events in the series, the variation of rainfall magnitude is plotted against the corresponding T on semi-log or log paper. The rainfall magnitude for any recurrence interval can be determined by extrapolating the plot between magnitude and recurrence interval. Empirical procedures can give good results for small extrapolations, but the errors increase with the amount of extrapolation. For more accurate results, analytical methods using frequency factor are used.
Different types of rain gauges. A rain gauge is an instrument to measure the precipitating rain in a given amount of time per unit area. Measuring rainfall can be primarily done in a different ways using different types of rain gauges. Rain gauge standard. The recording of rainfall using the standard or funnel rain gauge is generally done manually. These gauges work by catching the falling rain in a funnel-shaped collector that is attached to a measuring tube. Magnifying the rain in this way allows precise measurements down to a 100th of an inch. The amounts that exceed the tube capacity are caught in the outer shell of the gauge, allowing the recorder to pour out the liquid in the tube and fill it back up if needed. Non-recording gauges. Non-recording type rain gauge is the most common type of rain gauge used by meteorological department. The example of non-recording gauge is Simon's rain gauge. In this gauge, a funnel is provided with a circular brass rim which is 127 mm exactly so that it can fit well into the vessel. This funnel shank is inserted in the neck of a receiving bottle which is 75 to 100 mm high from the base section and thinner than the cylinder that is placed into it to receive rainfall. A receiving bottle has a capacity of 100 mm, and during heavy rainfall, the amount of rain is frequently exceeded, so the reading should be measured 3 to 4 times in a day. Water contained in this receiving bottle is measured by a graduated measuring glass with an accuracy up to 0.1 mm. Three types of recording gauges are tipping bucket, weighing bucket, and floating or natural siphon. Tipping bucket. The operation of a tipping bucket rain gauge is quite different from the standard gauge. The receiving funnel leads to one of two small buckets. Filling of one bucket occurs at 100 of an inch. The result is a tipping of the liquid into the outer shell of the gauge that triggers the second bucket to take its place. The process then repeats itself that allows for the precise measurement of rainfall intensity and amount. This gauge has become standard for wireless weather stations. Weighing bucket. The universal weighing rain gauge is optimal for climatology use. This is because of a vacuum that accounts for the effects of the wind, allowing more rain to enter the gauge. These gauges are very precise in measuring rainfall intensity as the weighing mechanism at the bottom of the collector that can be used to measure the depth and time simultaneously. Recording is carried out much in the same way as the older versions of the tipping bucket gauges. Floating or natural siphon. The working of this type of rain gauge is similar to weighing bucket rain gauge. A funnel receives the water which is collected in a rectangular container. A float is provided at the bottom of the container, and this float raises as the water level rises in the container. Its movement being recorded by a pen moving on a recording drum actuated by a clockwork. When the water rises, this float reaches to the top floating in the water. Then a siphon comes into operation and releases the water outwards through the connecting pipe. Thus, all water in the box is drained out.
What if there is a missing rainfall data? So now, let's talk about estimation of missing rainfall data. Sometimes, it may not be possible to measure the rainfall at a particular measuring station due to absence of the observer or instrument failure or any other reason. In that case, the prediction of the missing data can be made with the help of available data of nearby measuring stations. The following methods are generally used for computing the missing rainfall data. Arithmetic mean method. Missing precipitation P sub x of a station x is computed by simple arithmetic average of the rainfall at the nearby stations known as index stations. The formula for arithmetic mean method is P sub x is equal to the summation of P sub I over n as I goes from I to 6 is equal to 1 over n times the quantity of P sub 1 plus P sub 2 till P sub n, where n is the number of index stations. The arithmetic mean method is used only under the following conditions. The normal annual rainfall of the missing station should be within 10% of the normal annual rainfall of the index stations. Data of at least 3 index stations should be available, and the index stations should be evenly spaced around the missing station and should be as close as possible. In this method, the rainfall of the surrounding index stations is weighed by the ratio of normal annual rainfall. These are the formula used for normal ratio method. The normal ratio method is used under the following conditions. The normal annual rainfall of the missing station differ more than 10% of the index stations. Data of at least 3 index stations should be available, and the index stations should be evenly spaced around the missing station and should be as close as possible. Inverse distance method. In this method, the coordinate of the missing station is taken as 0, 0. Then, the coordinates of surrounding index stations x sub I, y sub I are found. The weightage of each index station is represented by the inverse of its distance from the missing station. The missing rainfall data of the station X is given by this method gives good results and acceptable for scientific analysis.
Converting point rainfall to aerial rainfall. A single point precipitation measurement is quite often not a representative of the volume of the precipitation falling over a given catchment area. A dense network of point measurement and/or radar estimates can provide a better representation of the true volume of the given area. A network of precipitation measurement can be converted to aerial estimate using any of the number of techniques, which includes the following. First, arithmetic mean method. This technique calculates aerial precipitation using arithmetic mean of all the points or aerial measurement considered in the analysis. The arithmetic mean method is the simplest method of estimating average rainfall. When the area of the basin is less than 500 square kilometers, this method implies summing up of all the rainfall values from all rain gauge stations and then divide it by the number of stations in that basin. The formula for arithmetic mean method is given below. The method becomes very clear by the use of tabular form. Here's an example. Thyssen polygon method. This is a graphical technique which calculates station weight based on the relative areas of each measurement station in the Thyssen polygon network. The individual weights are multiplied by the station observation and the value are summed to obtain the areal average precipitation. Average rainfall can be computed by the expression This method is very accurate than the first method. It is used for basins having areas between 500 to 5,000 square kilometers. This method can be best understood with the help of figures. Graphing Tyson polygon method. First, join the adjacent rain gauge stations. Second, construct the perpendicular bisector of each of these lines. Third, the polygon formed by the perpendicular bisector around a station enclose an area which everywhere closer to that station than to any other station. Fourth, find the area of each polygons shown in the figure. Fifth, compute the average precipitation using the formula. Here's an example. Isoheital method. This is a graphical technique which involves drawing estimated lines of equal rainfall over an area based on point measurement. The magnitude and extent of the resultant rainfall areas of coverage are then considered versus the area in question in order to estimate the areal precipitation value. An isoheight is a line on the rainfall map of the basin, joining places of equal rainfall readings. An isoheital map showing contours of equal rainfall present a more accurate picture of rainfall distribution in the basin. The isoheital method is the most elaborate and accurate than other two methods. The average rainfall can be computed by the expression. How to get the areal average precipitation using the isoheital method? First, from the rainfall values recorded at various rain gauge stations, prepare the isoheital map. Second, measure the areas enclosed between successive isoheights with the help of planimeter. Third, multiply each of these areas by the average rainfall between the isoheights. And lastly, complete the average rainfall by applying the given formula. Here's an example.
Double mass analysis. It is used to detect if data at a site have been subjected to a significant change in magnitude due to external factors such as problems with instrumentation, observation, practices, or recordings condition. So when we say double mass analysis, it is commonly used data analysis approach for investigating the behavior of records. And it is also to determine whether there is a need for correction of the data. A test for consistency. This step is a preparation of data whenever adjustment of precipitation records are needed. This is also used to evaluate a station consistency. Applicability of double mass analysis. So these are the limitations on using double mass analysis. First is, the base station should be located relatively close to station being tested. Second is the method should not be used in mountainous area where precipitation can deviate significantly for nearby station.
And the last one is this method should only be used for long-term adjustment of precipitation. So here are the things that we need to remember in using double mass analysis. First is, this analysis is obtained by plotting or making a graph. For the x-axis, we have the average accumulative precipitation of nearby station. And for y-axis, we have accumulative precipitation of the station under consideration or the station being tested. Next is to arrange the data from the recent or the latest year up to the past year. After arranging the data, we need to draw the mass curve. This is the formula for correcting precipitation data. Corrected precipitation is equal to original recorded precipitation multiplied by corrected slope over original slope, or P sub Cx is equal to P sub x times M sub C over M sub A.